Use a tree diagram. Now you may remember tree diagrams. They kind of look like factor trees, sort of. To find the number of possible outfits you can make using one shirt and one pair of shorts. Now, in your closet, you have all of 3 shirts and 4 pairs of shorts. So let's see how many outfits you can make. So just for clarity, we're gonna label the shirts as 1, 2, 3, and the shorts, since we have 4 pairs, as A, B, C, and D. Just to kind of try and keep it clear. I know some of you do. But we have to use a tree diagram to show it. So we can make a tree diagram going down, or you can make it to the side. We don't have a lot of room to go to the side, so we're just going to make one going down here. So I'm going to start with the shorts. I have 4 pairs of shorts to start with. Spread them out a little bit. Those are my shorts, A, B, C, and D. If I pick shorts A, how many shirts could I put with them? Right, so I'm going to branch off those 3 shirt choices. So I could put shorts A and shirt 1, or shorts A and shirt 2. See what I'm saying? If I decide to choose shorts B, I still have 3 shirt choices. Same with C, and same with shorts D. So if I look at this, I've got this combination, this one, this one, this one, this one, this one. How many do I have altogether? Options? 12. And really, you could do 3 times 4. Yes, you could. But we were asked to make a tree diagram. And then we count the branches, and there's 12 outfits. Okay? All right, now we have all these definitions. I typed them for you, just for the sake of time. An outcome is a possible result of an experiment. I have this big thing of dice or die. I don't know where it is, and I'm really bummed. So I think I loaned it to a teacher. But anyway, an outcome. Okay, you're not going to sit there if you're going to be distracted. Okay? I need you guys to pay attention. You were talking, you too, just now. I'm saying, I know you're not in your seat back there. I'm glad. Outcome is a possible result of an experiment. So let's say you roll a die. How many possible outcomes are there? 6. It has 6 ways it could land. That's what outcomes mean. Okay? Event. An outcome or collection of outcomes such as rolling an odd number. So you're going to see this writing all the time. What do you think that P stands for? The probability, exactly, of rolling an odd number. So that's the event that you want. Okay? Now let's say you're rolling a die and you see something like this. This is the event I want from rolling a die. What do you think that means? Right. This means I'm going to roll it twice. I want to know the chance of getting a 3 and then a 5. That's what that means, probability. Okay? So you'll see stuff like that. Sample space is the set of all possible outcomes. That's what we did right here. Set of all possible outcomes. Probability of an event is a measure of the likelihood or chance that the event will occur. So, give me, and this is stuff that we know, not everybody knows a deck of cards, I understand that, but those of you that do, what would be the probability of pulling a heart? How many hearts are there? Yeah, there's 4 different suits, correct? So out of this deck of cards, there's actually 13 hearts. So you could look at it like this, or you could just say there's a 1 out of 4 chance, because there's 4 different suits. Okay? Yep. Theoretical probability. We actually used theoretical probability to come up with that answer. It was stuff that we know. We knew there's 4 different suits in a deck. We know there's 13 hearts in a deck of cards. Those of us that play cards. Theoretical probability is based on what you know already. You don't need to conduct an experiment. So what's the probability of drawing a queen out of a deck of cards? How many queens are there? 4 out of 52. So it's a 1 out of 13 chance. Because we know that. We don't have to conduct an experiment to find that out. That's theoretical probability. Experimental is when you do have to conduct an experiment. The probability of an event occurring using repeated trials. So let's say we have this big bag of M&Ms.
So
And we're gonna conduct 100 trials and see how many times we pull a green out.
How many are in?
I don't know. Well, we have to know how many. We don't know. So you would have to just conduct a bunch of trials and find out what the probability is of you getting a green. That's experimental. We don't know, so we have to conduct an experiment. Okay? All right. Odds. Put a star. They are very different from probability. In probability, you always use the total chances on the bottom, right? There's 52 cards total. 52 cards total. There would be a 1 out of 6 chance of rolling a 3. There's 6 total ways. Odds, you don't use the total on the bottom. Different than probability, you don't use a total on the bottom. You put the number, and I'm going to show you this on the back side. The number of, for odds against, it's the number of unfavorable outcomes over the number of favorable. And they add up to the total. Have you ever heard, like, horse betting? And the odds in favor of some horse's name. This is what they're talking about. They're not talking about probability. They're talking about odds. Okay? Odds in favor. The number of favorable outcomes over the number of unfavorable. So it's not using the total, but when you add these two numbers up, you get the total. So for example, we know we have a 1 out of 4 chance of pulling a heart, right? Well, if I was going to write odds in favor, I would say 1 to 3 is what I would say. But let's look at it like this, not reduced. How many hearts are there in a deck of cards? 13. 13 ways I can pull one. How many are not hearts? 52 minus 13, which is what? 39. This is odds in favor of pulling hearts. So you don't use a total on the bottom. The ways it can happen to the ways it can't. That's the difference. Okay? So let's practice some of this stuff. So what's the probability of a traditional family having 4 girls? You can't just write this with one fraction. You have to do some work to get to that answer. So look at it like this. First child, what's their chance of having a girl? 1 out of 2. Second child, what's their chance of having a girl? Third, see where I'm going? And fourth, 1 out of 2. Now you multiply these together to find out the chance of getting 4 girls. So it's 1 out of 2 to the 4th. What's 2 to the 4th? Anybody know? 2 times 2 times 2 times 2? Somebody can do that in their head. I know you can. What's 2 times 2 times 2 times 2?
16.
Thank you. You got a 1 out of 16th chance of that occurring, having 4 girls. So sometimes you have to write it out, individual events occurring, and then multiply them together to find out the chance of that actual thing happening. Okay? All right, turn it over. All right, you flip a coin twice. How many possible outcomes are in the sample space? List the possible outcomes. Now, some people can just do this in their head. I like to make sort of a diagram for myself. So on the first flip, what can I get on a flip of a coin? Heads or tails, right? Then on the second flip, if I've already done a heads, I could get a tail or a heads on the second flip. Heads first, then tails. Heads first, then heads. But if I flipped a tails first, and I still have a heads or a tails for my second flip. So if I go across all these branches, then I can list all the possible outcomes. Heads first, then tails. Heads, then heads. Tails, then heads. And tails, then tails. How many possible outcomes? 4. Okay? You see that? All right. Let's look at some probability here. A department store is offering a discount on sunglasses. So they've got this big table spread out, all these different sunglasses on there. This table right here shows the number of each type of discounted sunglasses. You choose a pair at random, so you close your eyes and you pick a pair off the table. What is the probability that the pair you choose is polarized? So in order to find probability, you need a total of all the things you can choose from. So number one, find the total number of choices. So I've got 8 green polarized plus 4 brown polarized plus 7 green mirrored plus 9 brown mirrored. What is my total? Making you work. Thank you. So there's 28 of them laying out on the table there. Second, how many are polarized? Correct. How many are polarized? 8 plus 4 is 12. So find the probability of you picking a polarized. Probability of picking a polarized is equal to 12 ways out of a total of 28 to choose from. This is probability, so you put the total in the bottom. You reduce that. 3 out of 7. So you have a 3 out of 7 chance of picking. That's a pretty good chance. It's almost half. Now, do we always have to write probability as a fraction? Sometimes you'll see it as a what? Percentage. Most of the time here we're working with fractions. How would you get the percentage? 3 divided by 7 and then change it to percentage. Okay? All right. So here we're going to talk about theoretical and experimental. A bag contains 1 blue, 1 green, 1 yellow, and 1 red ball. Wait a minute here. This is what we know. We know this for sure. A ball is drawn at random from the bag and then replaced. The table shows the results for 24 drawings. So they took a marble out, and they put it back in. Then they took another one, put it back in. And they recorded their results here for 24 draws. For which color of ball is the experimental probability, that would be this right here, of the drawing, the color as the same as the theoretical probability? This is based on what we know. So let's start with theoretical. What is the probability, based on what I know, of pulling a blue ball? 1 in 4. What's the probability of pulling a yellow ball based on what I know? 1 in 4. So the theoretical probability of any color is 1 in 4 for any color. Okay, so I needed to know that. Now let's see how close our experiment is to that theoretical probability. How many total draws did we do? We did 24, right? So we got 4 blues out of 24 draws. We got 6 green out of 24. We got 9 yellow out of 24. And 5 out of 24 were red. So I want to see which one of these matches that. What's this reduced? Keep going. 1 out of 6. So it's not that one. What's that one reduced? Oh, we have a winner. Chicken dinner. Winner, winner. Right? This one doesn't work and that one doesn't work. So it says, for which color of ball is the experimental probability of drawing the color the same as the theoretical? So it was for the green ball. Green matches theoretical. Okay? Now we're almost done. Using the above example, find the odds in favor. Oh, odds is different. Be sure you are aware of that. Drawing a yellow ball. Now we've got two different probabilities here. We got this and we got that. I'm just going to use both of them. I'm going to start with theoretical. So odds in favor of drawing a yellow. So you need to put the ways it can happen, the favorable ways, over the unfavorable. So how many ways, based on what we know, can we draw a yellow? It's only one yellow, right? How many are not yellow? 3. So the odds in favor are 1 to 3, not 1 over 4. Common mistake. I see it in Advanced Algebra 2. People constantly want to write odds as probability. It's different. These have to add up to 4. Okay? One way you get a yellow ball, 3 ways you don't. You can write it as a fraction, or sometimes you'll see it written like that, 1 to 3. Now, we could also do it with experimental. So I want you to write down what are the experimental odds of drawing a yellow in favor. Odds in favor. How would that be written? You try it. Write the odds in favor based off this experimental results of drawing a yellow. Just do it. I'm going to wait for everybody to try it. Odds in favor of drawing a yellow based on these experimental results. Write it down. Can you wake her up? Okay. Okay. How many times did it really happen? How many times then did it not happen? Was it not yellow?
15.
Correct. Okay. 9 favorable, 15 unfavorable. Then you reduce that. So based on the experimental, it was 3 to 5 odds in favor of a yellow. See what I'm saying? Okay. I'm going to have you work on some of this first. So